So recording started now. So lecture number 9, 210 fluid mechanics, conservation of mass. So when we apply this for conservation of mass, what we do is we take capital B as M. That's the extensive property we're interested in. And then automatically the beta, which is the corresponding intensive property, that becomes 1. So in that situation, let's apply the RTT. So capital B for the system is M for the system. And on the right hand side, you have d by dt of integral over the control volume rho, and beta in this case is simply 1, then the integral over control surface rho times 1 times v dot n times dA. So that's going to be our Reynolds transport theorem for the conservation of mass. And we also know that in this case, from the definition of a system, dm by dt of the system is 0, because a system is a collection of molecules. And if you take the rate of change of the mass of a collection of molecules, that will be 0, because there is no nuclear reaction as such happening. So their mass will be constant. The collection of molecules that you've taken as a system, their mass will be constant. So this is 0. Yeah, that's the whole use of having a Reynolds transport theorem, because the physical laws or other laws can basically be applied to the system rate of change. So this ultimately results in the equation okay. So this is the conservation of mass in the control volume sense. Conservation of mass in the system sense is the collection, the mass of a collection of molecules or the mass of a collection of particles does not change with time. It's conserved. In a control volume sense, this is how we write the conservation of mass equation. Okay, so that's what we discussed in the beginning, that in fluid mechanics we work with control volumes. So the form of the equation will get slightly complicated. Otherwise, everything else is the same. Right? Any questions? Good. Now, this is the most general sense. Now, in most situations, you will have control volumes that will not deform. So, if you have a non-deforming control volume, then in the first term, you can take the d by dt inside the integral. So, it becomes partial by partial t of the density rho times d omega. Okay. So this we discussed. This can be done if your control volume is deforming. So we'll also tend to use. So I'll call this A, and this becomes A1. So we'll tend to use the A1 form in many situations when the control volume is non-deforming. Okay. Now another sub situation is when we have steady flow. A steady flow means, let's write it here. It's a sub situation of non-deforming control volume. So in this case, the control volume is also non-deforming, plus the flow is steady. So steady flow, we talked about that partial by partial t of anything will be 0. That's what the definition of steady flow is. So in that case, your first term where you have partial by partial t of rho, that will be 0. So the only term left is this one. So this we'll call A2 form. Okay. So all that is telling us for the conservation of mass situation is that whatever mass is entering is equal to the mass leaving. Because in this case, there is no mass of the molecules changing, that is by definition of the system. And in the control volume, we are saying that the density is not changing with time. So if inside a volume where you have some mass at any given time, if the density is not changing, so that means whatever is entering is equal to whatever is leaving. Right. And yesterday we also wrote that as a 1D approximation, where we instead of thinking of the inlet and outlet happening in many directions, it happens, we only talk about the normal outlet. So this can also be written as summation over all outlets, and then we have rho, the normal velocity Vn, and this is equal to summation over all the inlets. That's another way to write this. And this rho AV, or rho times Vn times A, is simply the mass flow rate. So all we are saying is that the mass flow rate out is equal to mass flow rate in. Because if things were collecting inside, if it was, for example, a gas, and there was no mass flow rate out, there's only mass flow rate in, you're charging a cylinder of gas. So when you put in more gas, as the amount of gas inside the control volume increases, then what's going to happen is the density will change. As you are feeding in more and more gas, its density is increasing. In the same volume, you have more mass now. So that this term, del rho by del t, in that case will not be 0. It's not a steady state situation. But for a steady state situation where partial by partial t for rho is 0, then the only way that is possible is when the net mass inlet is equal to mass outlet. So that could be a different situation where you also have mass leaking. Okay. Right. So this is steady flow. Now, what if your density was homogeneous? So homogeneous means it does not change with space. So whatever your control volume was, the density is the same everywhere. Whatever point you take, the density will come out to be the same. It's homogeneous. It's the same at all points in space. So if that is the case, then you can simply write this, you can basically cancel out the density on both sides, because it's the same at all outlets, it's the same at all inlets, so you can take it out as a constant rho. So this cancel. So we are basically I'm giving you a flavor of all sort of forms of the equation, whichever works.
So if density is heterogeneous, but in this our case, like d rho by dt is equals to 0, then like there is no change on the density now with the respect to time. So it always be homogeneous in the case of
Homogeneous is with respect to space. So homogeneous by definition means with respect to space, not time.
okay, sir.
So it can happen that so homogeneous means it's the same everywhere. But it's like a cylinder, for example, right? In a cylinder, if you are charging gas, then things are more or less homogeneous. But the overall density is changing with time. So all the values at all the points will increase with time. Okay, so they are unsteady but still homogeneous.
Okay, sir.
Okay, so these are different situations: steady flow, density being homogeneous. You have to understand what it means and then apply it in the continuity equation. Now, there are many situations where we deal with an incompressible flow. So, incompressible means density is constant, right? So, if you are dealing with a liquid, let's say water, then for a very large pressure, water will behave as almost incompressible fluid. So, that means your density can be taken as a constant. So, if density is taken as a constant, then del rho by del t will be 0 as well. For a different reason, the flow, the density is constant here. So with time, it's not changing; it's a constant. Right? So your conservation of mass equation again becomes this. Same form. And in this case, basically what it means is the net volume, or should I say, just the net volume out, volume flow rate out, is equal to net volume flow rate in. So that's meter cube per second. And this is also known as the continuity equation. It has another name. So if you have a control volume which has an inlet and an outlet, it could have multiple inlets, that's okay, or multiple outlets for that matter. So what continuity means, there's a continuity. Okay, there's no discontinuity as such. So whatever is entering is equal to whatever's leaving. There is no flow getting collected. There's no discontinuity. It's a continuous flow. Whatever enters is whatever leaves. Okay. So very often we'll refer to this equation where you have the net flow rate in is equal to net flow rate out as the continuity equation. Sometimes you'll see area times V equal to constant. That is also another way to write the continuity equation. Okay, so let's solve a problem. This is again an example from the book. So what we have here is we have a tank. So in this tank we have two inlets and there's no outlet. So we have inlet 1 and then we have an inlet 2. The velocities are v1 and v2. They're both normal velocities. So v1 in fact is 1 meters per second and v2 is half a meter per second. Now in this case the tank is not full, in the sense that up to some height there is water, and then above that you have air. So what will happen is when you you pump in more water, then the height will increase with time. And the tank of course has some sort of a cross section, where this cross section area A is 0.2 meters square. Okay. The diameter, so the inlet and outlet, they're both circular in cross section, and the diameters are D1 is 2.5 centimeter and D2 is 8 centimeter. Yes, it's a D2 is much bigger diameter as compared to D1. Is the problem clear? So what you have to find is, you have to find the rate at which the height of water in the tank will increase. Now I know that you can simply apply the volume inlet volume flow rate ideas and then calculate dH by dt. So basically there's you're feeding in more volume, so that is resulting in an increase in the height of the liquid. So we basically can find out the q1 q1 plus q2, that's the net volume flow rate that is into the into the tank, and that will result in an increase in the volume flow rate volume of the that will result in an increase in the volume of the water inside the tank. If you simply divide that by the area, that gives you the increase in the height with time. Okay, so this is a very simple problem, but I want to demonstrate the application of the transport theorem here. We might have more complicated situations where the density is changing and so on. That may become a bit more non-trivial. So let's apply the transport theorem and then see what we get. Okay, so let's write the transport theorem the way we apply it. So in this case, I mean, of course, dm system by dt is 0, so we have d by dt of integral over control volume rho d omega plus integral over the control surface rho v dot n dA is 0. So I'll start with the most general form. Now we'll simplify. I'll keep rewriting here. So the density in this case is, I mean, firstly the uh, control volume that we have taken. Let's take the control volume as the same as the tank volume that we have. Okay, so think of it as I didn't draw the complete tank, but it's the complete tank as the control volume. Okay, so that means that I can take the d by dt term inside because my control volume is not deforming, it's not changing with time. And this term actually is 0. Sorry, this is actually it's not 0 because you have two different fluids here. So in this case, this term that we have where you talk about the control volume, the control volume is the blue one that I've drawn. It has two fluids in it, and each fluid has its associated mass. So I'll have to add so some part of the control volume. So some of these integrals will come from air, some of these will come from water. So we'll do CV water and CV air. Now for the CV air, what we see is, in fact, I don't even need to write. I can keep the d by dt term outside for ease. So what this is telling us is the mass of air inside the control volume. Now that mass of air inside the control volume is not changing. You're simply compressing the air, because if you feed in more water, the air on the top will get compressed. Right? So its mass is not changing. So this term actually becomes 0, because rho times d omega integrated over the control volume for the air part is not changing with time. Okay. And the control surface term can simply be written as a sum of two terms, because we know that there's only two inlets, no outlet. And the inlet term is negative. So it's negative rho 1 V1 A1 minus rho 2 V2 A2. Right? Okay. So let's simplify this. So in fact, I actually did not need to write this outside. I can keep it inside only. It's much easier. So d by dt, and then I have rho times d omega of Cv of water. So this is nothing but the the, uh, the density times. Now in this case, we're talking about water, right? So the density of water is constant; it does not change with time. So it's incompressible situation. So water is incompressible. So I can take the rho term out of the integral first. It's a constant, and I can also take it out from d by dt. So all we are left with is d by dt of the overall volume of the control volume, which has the water part of it. So this is d by dt of the um, volume of Cv water, and this is equal to rho 1 V1 A1, and again rho is rho of water, right? So in this case, it's a constant plus V2 A2. So rho gets cancelled, and the omega, or the volume of water, can be written as the height h times the cross section area. So that becomes A times h. A in this case is the area, the cross section area of the tank. That's pretty much it. So we have got what we wanted. So in this case, I can take the A out. So I get dH by dt. On the right hand side, you have V1 A1 plus V2 A2. This becomes And that is exactly what we started with in the beginning. If you put the numbers, this becomes 1.5 centimeters per second. You can check it yourself later. So in this problem, you should be clear with how we applied the transport theorem in this problem, in this case. So if you have any questions at any step, feel free to clarify. Okay. So if there's no question, then we'll move on. Now, the inlets and outlets we've been talking about, these small inlets or outlets, we have been taking, for example, V1, V2. But in reality, if you look at any pipe, like this, for example, so I'm zooming into a pipe. You have a pipe. So when we look at the flow profile inside pipe, we'll see that it is somehow parabolic, in the sense that on the boundaries, the flow, the x flow velocity is 0, and at the center, it has the maximum flow velocity. So what is the meaning of this V1? Of course, it's some sort of an averaged velocity, because if you were to actually measure, if I was to give you a pipe and say, tell me what V1 is or V2 is, how would you, you would calculate a parabolic profile, because you'll see that the velocity will be a function of the radius, where r is, for example, this. So how do you um, calculate this uh, u as a function of, this average velocity in this case? Okay, so what do we need? I mean, ultimately, all we want to talk about through this average velocity is a volume flow rate. Okay, that's the aim. So what we are doing is we're trying to calculate the volume flow rate, and volume flow rate is, the way we calculate that is, we say that it's the V average. So we are trying to identify an average velocity. So we are saying, use the black color, volume flow rate for all the expressions we have been writing, the 1D approximations and so on, is equal to the area of cross section of the pipe times the average velocity. So that's what we are using the average velocity for getting the volume flow rate. Because in the expression, in the control surface integral, that v dot n term that we have, there we need an averaged velocity. Okay. So, and if you were to calculate the volume flow rate using a proper integration here, in this pipe situation that I've shown you, then at different cross section areas in the pipe, you see that the velocities are different. It's maximum at the center and it's 0 on the boundaries. So for that matter, we'll have to integrate, and the integral happens over an infinitesimal area in the cross section of the pipe, and this is equal to V for that area, and you integrate over the area A of the pipe, A of pipe, or inlet or outlet, whatever you want to call it. Okay, so just remember this, that whatever average velocities you talk about in the inlet and outlets is actually calculated. If it's given in the problem, then that will be actually an area averaged. So if you were setting up your own problem, hypothetically, then you'll have to supply the average velocity values by using this idea. And if it was a circular pipe, then your integral becomes much more easier to work with, but that you can figure out yourself. So many times we have this confusion as to what does the average velocity mean. So this is what it means. Is that clear? Very good. So let's now apply the Reynolds transport theorem to the linear momentum to get the linear momentum equation. So again, the way we did it earlier, so capital B in this case is a linear momentum, that is mass times velocity. And remember, this velocity is a function of space and time. So this is a velocity field we're talking about. Just remember this, don't get confused with what is this velocity. So this is our capital B, and beta then becomes simply the velocity field B. So let's apply the RTT. So this is d by dt of capital B of the system, and that's d by dt integrated over the control volume rho times beta. Beta in this case is V times d omega. And then we have the control surface term rho times beta times V dot n dA. So that's the Reynolds transport theorem written for the linear momentum, that is capital B being the linear momentum. So so beta becomes the velocity field V. Now it's a bit confusing because you have two V's here, unlike in the last case where you had the mass, that was, so beta was 1. So it becomes a bit confusing. So remember what happens in this control surface term is that this V dot n term is resulting in a flux in or flux out of the control surface. So this V dot n term results in some sort of a transport. And this rho times V, or this rho times beta term, is the quantity being transported. So for the case of mass, you were transporting mass. Okay, you're transporting some amount of fluid. So if a fluid moves in or out, its mass moves in or out. So the quantity being transported was mass. In case of energy, I've not done it, but we can use capital B equal to energy. So in that case, the quantity being transported is energy. In case of momentum or linear momentum, the quantity being transported is linear momentum, which has basically m times v. So the velocity which is resulting v dot n, that's resulting in a transport. In this case, it's actually transporting momentum, which has v in it. So it becomes a bit confusing, but remember this idea that v dot n is the term resulting in a transport, because if v dot n was 0, then there is no movement of fluid in or out. Either the fluid has no velocity at all, or its velocity is completely tangential to the surface. that will not result in any flux out or flux in. And this second term that we have here is the quantity being transported. So many people have this confusion, so I thought of clarifying it, but we can always think about it later. Right. Now again, as earlier, the reason we use the Reynolds transport theorem is because it helps us apply the physical laws, and the rate of change of the linear momentum of a system is nothing but the net force acting on the system. So this allows us to write the linear momentum equation for fluids in the control volume sense. The net force acting on a fluid is the sum of these two integrals. So that will become our linear momentum equation for fluids. All right. So like we said, the net force is mass times the acceleration. For fluids, this is the form of the linear momentum equation that we'll tend to use. Now, of course, this net force has to be figured out. And net force can usually be split into two types, as I've discussed already. One is body forces. So forces which act on the amount of fluid you have. So for example, mg. Okay, more the mass in more the volume, in the sense of more the mass, the more the force. It could be electromagnetic force. More the charge, more the force. So these are because of the amount of material contained. And the other type is the surface forces, which include forces such as pressure, normal reaction, and so on. So these forces act on the surface. So it depends on the amount of surface exposed. So if you when you have to solve this, when you have to use this linear momentum equation, you'll have to think of all the forces acting on the system. So that will have to be split into two types, and then you add them. We are almost out of time now, so I would want to stop here. And in the next lecture, next week, I will expand further on this and help solve a problem to clarify the usage of the linear momentum equation in fluids. Okay, so we will stop now. In case anybody has any question, please feel free to ask.